In section 5.3, we are going to look at binomial probability distributions. A binomial probability distribution is a special type of discrete probability distribution. In section 5.2, we looked at discrete probability distributions, and so now we're going to look at specific ones that are binomial. You might want to make a note that it is a special type of discrete probability distribution. We will know that a probability distribution is binomial if it follows the binomial settings. There are 4 of them, and we use the acronym BINS to remind us of the 4 things that they need to fulfill. The first thing is that it needs to be binary. Therefore, what it means is that the trial must have 2 possible outcomes. This is usually referred to as success or failure. Some things may not seem to be binary, but we can often set them up to be binary. For example, if we're talking about the color of shirts that people are wearing, there are multiple colors that people could be wearing. That would not be binary. However, if we phrased it as the number of people that are wearing a green shirt, then we can talk about it as people who are wearing green shirts and people who are not wearing green shirts. And therefore, it would be binary because there are 2 outcomes, green or not green. The next thing is that the trials need to be independent. What that means is the outcomes of one trial does not affect another. If we are talking about a deck of cards and you pull a card out of the deck, if you put it back, then the trials are independent of each other when we select another card. But if we pull a card out of our deck and then select another card, the trials are now dependent on each other because the outcome of the second draw of the card changes based on whatever you select the first time around. Our N represents the number. The procedure has to have a fixed number of trials. For example, we're going to select 5 cards, or we are going to roll a dice 10 times. That would be a fixed number of trials. And then for the S, successes, the probability of success, we use P to identify it, it must remain the same in all trials. Therefore, the probability cannot change from one trial to the next. That is part of the reason why the trials need to be independent. The probability of success when we have dependent events changes the probability. So example number 1 just wants us to try and determine whether the random variables that are given have a binomial distribution or not. If we roll a fair die 10 times and let x equal the number of 6s, we're going to have to look at our B, our I, our N, and our S. If it fulfills all 4 of these things, it is binomial. For B, are there 2 possible outcomes? Well, our outcomes here are going to be either rolling a 6 or not rolling a 6. Therefore, we would say that the B is satisfied. This is binary. For the I, our outcomes need to be independent. Well, the outcomes are, in fact, independent. since one roll has no effect on another roll. The outcome of the first time we roll the dice does not affect the outcome of the next time that we roll it. Does it have a fixed number of trials? It told us we're going to roll it 10 times. Therefore, 10 rolls is a fixed number. And the probability of success. Does the probabilities of success remain the same? Yes, it is remaining the same. The probability of rolling a 6 is always going to be 1 out of 6. So the probability of success is 1 out of 6 for all trials. Since this fulfills all 4 requirements for a binomial setting, we can say that this is a binomial distribution. For B, we are shooting a basketball 20 times from various distances on the court. Let Y equal the number of shots being made. For our B, is it binary? Well, our outcomes are going to be either we make it or we miss it. Therefore, it fulfills our B. Are the trials independent of each other? Or are the outcomes are they independent? Yes, our outcomes are independent. If you make the first shot, it has no bearing on whether or not you're going to make the second shot. N, are there a fixed number of trials? Well, the problem said that we're going to shoot the basketball 20 times. 20 is a fixed number of trials. And then for our S, our probability of success. In this case, is the probability of success the same? Since it said that we are shooting from various distances, our probability of success is not the same. So the probability of success is not the same in all trials, since the distance is changing. As a result, this fails that the probability of success must remain the same, and this is not a binomial distribution. For C, it said to observe the next 100 cars that go by and let C equal the color. So the first thing we're going to look at is this binary? So B, what are our outcomes? Our outcomes are whatever color the car is. The car could be red, white, black, green. There's many different outcomes. Therefore, this is not binary, since there are more than 2 colors of cars. Therefore, we would conclude that this is not a binomial distribution, since the binary part is not fulfilled. Now, what if we were interested in the probability distribution of Y, where Y is the number of heads that are observed in 10 coin tosses? Listing the outcomes in this experiment would be a burden, since there are 1,204 of them. Let's list 2 items in this sample space. Since we are flipping the coin 10 times and there's 2 possible outcomes, the way that we find the sample space would be taking 2 to the 10th power. And 2 to the 10th power is 1024. So if we wanted to write out our entire sample space, it would take us a long time. Some examples of items that are in that sample space would be 10 heads. That would be one example of an element in the sample space. A combination of heads and tails. Maybe it was 3 heads and then a tails and then another heads and then 2 tails and a heads and 2 more tails. Any combination of heads and tails, as long as it equals a total of 10, is an item within that sample space. When we looked at discrete probability distributions in the previous section, we saw that the easiest way to make that probability distribution is to write out the entire sample space, and then we could count up how many options there are and create our binomial distribution, our probability distribution in that way. But thankfully, if an experiment follows a binomial setting, we can use the following formula in order to go ahead and write out what the probability of different things happening. Instead of having to write out all of the 1024 different outcomes in our sample space, we could just use this formula. The formula looks a little scary, but it's not all that difficult. So the probability of x is equal to n factorial over n minus x factorial. Well, that is simply our combination formula. From chapter 4, this is the combination formula. So you can just use your calculator and use that C button, and it makes things easy. And there happens to be a typo in it, because it should be n factorial divided by x factorial times n minus x factorial. Then we multiply by p to the power of x times q to the power of n minus x for every x value from 0 all the way up into however total number of trials we have. Now, what do each of these variables mean? The first one is n. N is the number of trials. And our n goes in various places within our equation. The next is the x. X is the total number of successes. So how many times we are successful. P is our probability of success. So what's the probability that we are successful in any one trial? And Q is the probability of failure. One easy way that we can find the probability of failure is to take 1 and subtract away our probability of success. That will give us our probability of failure. Whenever we are going to be solving one of these problems, we always want to round to at least 3 significant figures, if not more than 3 significant figures. Now we're going to look at an example. In a board game, 2 6-sided dice are rolled. Let x equal the number of 7s, meaning the sum of the 2 dice is 7, rolled in 4 rolls of the dice. Find the following probabilities. We're going to use our binomial formula. Let's think first. Okay, we need sums of 7. So if we're going to roll 2 dice, we can get outcomes of 1 through 6 on the first dice and 1 through 6 on the second dice. If we get a 1 and a 1, our sum is 2. A 1 and a 2, our sum is 3. There are 36 outcomes. Out of the 36 outcomes, there are 6 different ways in which we can get a sum of 7. Our n, we want to look at how many times are we rolling the dice? How many trials are we doing? And it said 4 rolls of the dice. Our n in this case is going to be 4. What is our probability of success, or our P? Well, our probability of success, the probability of rolling a sum of 7 is 6 out of 36. Or we could reduce and write that as a 1/6. We don't want to write it as a decimal because this is a non-terminating decimal and we want to use the entire thing, not a rounded value. So we're going to leave it as a fraction. And then for our Q is going to be 1 minus the probability of success. 1 minus 6 over 36, or 1 minus a 1/6, is going to give us 5/6. Now, in order to go through and complete this problem, all we have to do is use our formula. Our formula says NCX times the probability of success to the power of x times the probability of failure to the power of n minus x. If we want to find the probability that x is equal to 0, that means that in our 4 rolls, we get no sums of 7. We just have to go ahead and use our formula. The probability that x is equal to 0 is going to be 4 choose 0 times our probability of success. Our probability of success was 1/6 to the power of 0 times our probability of failure, which is 5/6 to the power of 4 minus 0. And then all we have to do is use our calculator to calculate this. I'm going to put in 4C0 times 1/6 to the power of 0 times 5/6 to the power of 4. And we end up with 0.48225 and so on. So we're going to say that our answer, the probability that x is equal to 0, is 0.482. We always want to round to at least 3 decimal places, if not more. For the probability that x is equal to 1, we want to do the exact same thing. The only thing that's going to change is that our x value is now going to be 1 instead of 0. We will have 4C1 times 1/6 to the power of x, which is 1, times 5/6 to the power of 4 minus 1. If we use our calculator for C1 times 1/6 to the first power times 5/6 to the third power. That gives us 0.3858. We could round that to 0.386. So the probability that x is equal to 1 is going to be 0.386. This is much easier than writing out all of the 1,024 possible outcomes, which this one actually doesn't have 1,024 outcomes, but it's better than writing out all of the different outcomes. Now, for the probability that x is equal to 2, again, just use our formula. So 4C2 times 1/6 to the second power times 5/6 to the power of 4 minus 2. Use your calculator, and when you use your calculator, you get that the probability that x is equal to 2 is 0.116. We could keep going to fill out the entire table. Since our situation had 4 rows, we would have 0, 1, 2, 3, and 4 as our x values in the table, and then the probability values would be in the second column. Now, when we look at something like D down here, where it says the probability that x is greater than 2, well, the probability that x is greater than 2 is everything except for these 3 things. It's the probability of getting 3 that add to 7, plus the probability that when we add them, 4 of them add to 7. Or in other words, we could use our complement. For this one, we're going to take 1. This is equivalent to 1 minus the probability that x is equal to 0, plus the probability that x is equal to 1, plus the probability that x is equal to 2. So it's everything except for those 3 things. And since we already found 0, 1, and 2, all we have to do is take and add our outcomes and subtract them from 1. And we end up with the fact that the probability that x is greater than 2 is equal to 0.016. For part E, it says to make a table and a histogram of the probability distribution for x. We're just going to make a table for right now. Our x value, and it represents the sum of 7, or the number of sums of 7, and then the probability of x. So if we have 0, 1, 2, 3, or 4 sums of 7, probability of x for 0 we found already. It is 0.482. For 1, it is 0.386. For 2, it is 0.116. And then if we used our binomial probability formula with 3, we would end up with 0.015. And if we ended up with our probability value for 4, we do get 0.000772. This is the reason why we round to 3 significant figures, because there can be times where you're going to get very small probabilities. Sometimes I find that we get tripped up on just the wording. So let's make sure that we understand what the wording is referring to. If you see the words or less, for example, that is 8 or less. The way that we would write it is the probability that x is less than or equal to 8. So we have to include 8 in our sum. This would be all of the probabilities, 0, 1, 2, 3, 4, 5, 6, 7, and 8. Or more, whenever you see the words or more, for example, 4 or more, our notation is the probability that x is greater than or equal to 4. Since it says 4 or more, we include 4. More than 3 would be an example. That would be x is greater than 3. Since it is strictly more than, we cannot include 3. Less than, for example, less than 6, that's the probability that x is less than 6. At least, so the example, at least 7, that means you need 7 or more values. The probability that x is greater than or equal to 7. And then at most, so the most it can be, at most 9. So x cannot be greater than 9, but it could equal to 9. So x is going to be less than or equal to 9. So within these binomial probability formulas and just probability in distributions in general, you will see problems written and have some of these wordings. So that kind of tells you what you need to be looking at. Example number 4. Each wiener dog puppy from a particular pair of parents has a probability of 0.2 of being spotted. Suppose the parents have 10 puppies. Find the following. First off, we have to identify what our N, X, P, and Q are for our situation. Since they said they have 10 puppies, 10 is going to be our N. Our probability of success. What's the probability that they are spotted? Well, it has a 0.2 probability of being spotted. So our probability of success, or our P, is 0.2. We can find our Q by subtracting from 1. So our Q is going to be 0.8. Now, in part 1, it says find the probability that exactly one puppy has a spotted coat. 1 is our X. So in this problem, our N is 10, our X is 1, our P is 0.2, and our Q is 1 minus 0.2 or 0.8. So from there, all we have to do is use our formula and solve. We have 10C1 times probability of success to the power of x, which is 1 in this case, times the probability of failure to the power of n minus x, or 10 minus 1. So here, this is the probability that x is equal to 1. We use our calculator, and when we use our calculator, we end up with 0.268. For the second one, find the probability that 4 or less of the puppies have a spotted coat. Again, our N is 10. Our X this time is going to be less than or equal to 4. Our P is still 0.2, and our Q is still 0.8. So now, in order to find the probability that X is less than or equal to 4, we have to find the probability that we have 4 spotted puppies, plus the probability that we have 3 spotted, plus the probability that we have 2, plus the probability that we have 1 spotted, plus the probability that we have 0 spotted puppies. So essentially, this is just a lot of work for our calculator. All we have to do now is substitute an X being 4 into our binomial probability formula. So up here, our 1s are going to change to 4s. And when we do that, we end up with a probability of 0.088. Plus, then we're going to plug 3 in for our X in all of these places where there's a 1. And we end up with 0.201, plus then we put 2 in and we get 0.302, 1 in, which happened to be 0.268, and then we're going to substitute 0 in for our X, and we end up with 0.107. And as a result, the probability that our X is less than or equal to 4, when we add all of those things together, it is 0.966. And I'm going to leave 3 for you to try on your own. The final answer is 0.878. And also for 4, the probability that more than 2 of the puppies have spotted coats, that answer is 0.323. 5 says, if your parents are hip and allow you to keep 3 of the 10 puppies, how many different ways can you choose your 3 puppies? The order in which we are selecting them does not matter, so we can use combinations. 10C3, or there are 120 different ways that we can choose those puppies. Taking us back to chapter 4, and I just put that in the wrong place. It should go down here. Whoops. And then what would you name those puppies? And that's it for section 5.3.